Hello, myself Susobhan. My designation is Assistant Professor at SBIST and my department is ECE. Now I am going to discuss the various kind of steps in IC fabrications. So these are the outcomes which I have been included in this lecture. First one is the schematic of wafer, various components of wafer, the cross-sectional view of MOSFET. Then I also discussed about CVD process, chemical vapor depositions, patterning process, which is basically called the lithography. I will discuss later in this lecture. Doping process and various steps which are included in MOSFET fabrications. This is the schematic diagram of wafer have been shown over here. These are the basic structure of wafer. And this is called the notch point. From the helping of this notch, we can point or we can locate the particular orientations of integrated chips or die fabrications. Okay, these are the different kind of sectors are present over here. Each and every small box or sectors are known as die or chip, and each and every boxes form with respect to each other with electrical contacts. Some of the dies are used for testing purpose. If we observe in this diagram, we can see that some of the dies are not complete. Actually, each and every boxes or each and every die, a complete die is looking like a rectangle. But if we going to the surface of the wafer or the edge of the wafer, you can notify that some of the dies are incomplete. Okay, some of the dies are incomplete as compared to this complete die. So if you want to fabricate IC, the main starting material will be a wafer. This is nothing but a wafer is made by different kind of semiconductor material. But in IC fabrications, we can choose basically the available material, which is silicon. So the starting material always be wafer in IC fabrication, single crystal wafer made by silicon, and these are the end products which I told, the dies or ICs. All of these are the end products of fabrications, and the intermediate steps are referred to as wafer fabrications. Some common wafer terminologies are chip or die, device, then it will be device, then circuits. These are the basic steps or the common steps which are included in wafer terminology. And the terminology die and chip on the wafer surface are most commonly used and interchangeably referred to one standalone unit or wafer surface. This is the wafer, basic wafer, and these are the sectors, and each and every sectors are called die or chip. and each chips are connected to other chip by electrical contact. Okay. Now here one point have to notice that the area between the dies or chip is called scribe line. If we observe this point, the zooming point, this is called the area or the junction in between two dies, and this line is called scribe lines. Scribe lines, which is basically called the scribe lines. This is used for separating the individual dies when fabrication is completed. Scribe lines can be blank, but most often they consist of testing structures, and these kind of testing structures are basically known as electrical testing. This kind of testing structure is called electrical testing, and the end process is called the quality control process. There are also some edge dies or partial dies at the corners. If we observe across the corner, we can see there are some incomplete dies, and these are basically called the edge dies. And these dies can be used for making smaller testing circuit for process control. These dies are basically used for corner dies, which are incomplete dies, and these dies are basically used for process control, and we can also use testing purpose. We can use also this kind of dies testing purpose. This is the cross-sectional view of MOSFET by using different layering. Okay. From this description, we can also give a statement that larger the wafer size, if the size of the wafer is increased, more number of chips or dies can be manufactured. For example, for 300 millimeter wafers, this translates to a total 440 dies including edge chips, while with 450 millimeter wafers the total number of dies are 994. Area of wafer by area of die calculations. I got this kind of informations basically. There are a number of different steps which have been included in IC fabrications. Typically, a wafer can moves from one processing step to the next processing step, similar to an assembly line manufacturing. Different schemes for classifying the processing steps are available in IC fabrications. They are basically divided into four main categories. Number one is layering, second one is patterning, third one is doping, and last one is heat treatment. So this is the cross-sectional view of MOSFET showing with different layers. Here we can see that the polysilicon is used as a gate. This is the source terminal. This is one kind of MOSFET. If we observe this diagram, we can conclude that this is the MOSFET diagram. So the polysilicon is used as a gate with this silicon compound, and these are the interlayer dielectrics. Layering is the process by which all these different materials are added to the MOSFET. Okay. Here also highlighted the various thin layers are present in this device. These are the silicon dioxide layer, and this is all of these are dielectric layer, and this is the silicon nitride layer. This is the source terminal, this one is the drain terminal, and this is the terminal which sandwiching in between source and drain is called the gate terminal. So this is the complete configurations of a MOSFET, and the substrate chosen over here, p-type substrate. So obviously the channel will be made by n-type substrate. So the different layers help in defining the various components of MOSFET and obtaining a functional device. Example, for example, the passivation layer helps in electrically isolating the metal contact to the source, drain and gate. This is the passivations of layer. By using this layer we can isolate the metal terminal. This black terminal, this is basically called the metal terminal, from the substrate terminal, okay, which are basically known as source, drain and gate terminal. So if you want to isolate the metal terminal from the device, passivation layer help us, which are basically electrically isolated. In the case of grown and deposit layer, basically in the case of grown layer, the underlying wafer material, typically Si, made by Si, that would be consumed. This is basically formed by oxidations of Si into SiO2, and this is categorized into two types. Number one is dry oxidations, and number two is wet oxidation. In case of dry oxidations, the equations will be looking like this: silicon plus oxygen gas, and the component after reactions we will get silicon dioxide, and this insulating material deposited over here, over the surface area. But in case of wet oxidation, silicon react with H2O then we will get silicon dioxide and hydrogen gas, and this silicon dioxide deposited over here as an insulating layer on the surface of the material. So this is the common cross-sectional view of MOSFET with different layers. Layering operations are classified into two types. One is based on grown, another one is based on deposition. Growns are classified into two types, oxidations and nitridations, and depositions are basically CVD. It is classified into CVD, spattering, evaporations, etc. Electroplating. All of these are under deposition types. This is the process, the main process, which is called chemical vapor deposition CVD process, by which silicon's growth has been occurred. By using this process, polycrystalline silicon is formed across the output or after the reactions of the component, and which will be deposited on the wafer. And this kind of silicon can be doped and used as the gate terminal for the MOSFET. Silicon dioxide layer is formed on the surface. Silicon dioxide layer has been formed, basically I have shown over here. The silicon dioxide layer has been formed the surface of the material, and it is also consuming the underlying silicon layer. Okay, so CVD is basically takes place in the vapor phase, and it is very useful for growing polycrystalline silicon. And here silicon dioxide layer is formed, I already told, on the surface by consuming the underlying silicon layer. For further oxidation, the oxidizing species are basically used over here, oxygen and nitrogen. Sorry, oxygen and H2O, not nitrogen, H2O, has to diffuse through the oxide to reach the silicon surface. These are the wafer placed inside the furnace, and this is the input, gaseous medium or acid, and we can control it by changing the input of this gaseous medium or acid medium, and we will get silicon crystalline wafer across the wafer. This is the overview of patterning process, and this technology is basically called the lithographic technology, which is very, very important. Before going to lithography, I want to tell there are two kind of resist are basically used in lithography technique. One is positive photoresist, another one is negative photoresist. This is the diagram of semiconductor material. This is the silicon substrate which have been chosen over here, and the ground layer is silicon dioxide layer, insulating layer, which have been deposited by CVD technique. And over silicon dioxide, and another layer is formed, and this layer is consumed. This layer is formed by using photoresist, and these are the two types. The two kind of photoresist are basically used. One is positive photoresist and another one is negative photoresist. So in case of positive photoresist, this is one kind of photoresist in which the portions of the photoresist that is exposed to light become soluble. The exposure portion of the positive photoresist is soluble, but in case of negative photoresist, the exposure portion is not soluble. It is just the reverse of the positive photoresist. Okay, so patterning, this is one kind of lithography, is one of the most important steps in IC fabrications or wafer fabrications. By this kind of steps, we can selectively collect, mask and expose portions of the surface for deposition, doping or etching. It sets the critical dimensions of the device. The drive to pack more device in a chip, which are basically smaller device, is directly related to the ability of the pattern small region in the wafer. If the patterning is not proper, then we are not getting appropriate chip, and this kind of chips are basically called the defective chip. Okay, this is a very challenging work in semiconductor industry. The main challenge, the main goal is reduction of device size, and increase the performance or their ability by using this patterning. To make a pattern, we have to take a reticle at first. What is reticle? Reticle is nothing but it is the hard copy of the design that is transferred onto the chip. Reticle is nothing but this is the hard copy of the device. Here we can see this is the reticle that or pattern that is transferred into the chip. Okay, so this hard copy is generated by writing the pattern over here, writing the pattern, and if you want to write this kind of pattern by using reticle inside the chip, you have to use laser beam or electron beam, and is usually done by coated glass. Then the pattern obviously transferred towards the chip, and the pattern transferred depends upon the what kind of photoresist you have been chosen. Okay, this is the doping region in wafer. From this diagram we can see that this is the oxide layer which have been formed over the surface region, and this is the doped material. As the substrate is p-type, I told you in earlier lecture, as the substrate is p-type, obviously the doped channel or the doped material will be n-type. And here the oxide layer is used as a hard mask to control the region where doping is occurring. Now in this diagram we can see that this is the defective particles. These are the defective particles on patterning process or lithography process. Defects that cause the damage. These are the dust particles, and this is the pattern which have been transferred, you want to transfer over the surface of the semiconductor material. These are the dust particles which are included inside the patterns, and due to these particles what will be happened, we are not getting the actual pattern across the semiconductor surface which user or you want to transfer actually, and defects that cause damage to the IC, and this kind of defects are basically called the killer defect. This kind of defects are basically called killer defect. Okay. And these kind of defects are basically occur due to the reduction of size of ICs. If we reduce the size more, then we will get more defects, and that will be turned into killer defects. So that is why this is the very challenging things which is called the photolithography or pattern transformations. Now this is the diffusion technique. Basically diffusions are two types. One is thermal diffusions, another one is ion implantations. This is basically doping techniques. By using this doping we can diffuse material inside the semiconductor bead. So there are two main techniques for doping. One is thermal diffusions, which have been shown the figure A, and figure B shown the ion implantations. Thermal diffusions, it is nothing but the movement of dopant material. The movement of thermal diffusion is nothing but it is the movement of dopant material. This is the semiconductor bead. These are the two electrode terminals, and these are the dopant material which have been added to the bulk of the material, and this kind of diffusions of material basically occurred by thermally. The wafer has to be heated to high temperature around 1000 degree centigrade. This kind of process is happened over 1000 degree of centigrade. The wafer has been heated over this temperature. Then what will be happened? The material has been diffused across the bulk of the semiconductor. For N-type doping, if we used N-type doping, then we could use P2O5, pH3, this kind of material. But in case of P-type doping, we can use BCl3, B2O3. All of these are components, chemical compounds we have used for doping. Thermal diffusion is an isotropic process. Okay, this leads to lateral spread of the dopants. We can see from the diagram. After diffusions, after added dopants, they will be diffused and towards the bulk of the material, and it is one kind of isotropic process, and it is called the lateral diffusions. Gradually these dopants are spreaded or diffused across the bulk of the material or the wafer. But in case of ion implantations, this is one kind of doping procedure, figure B. In case of ion implantations, the dopants atoms are ionized and then made to impinge on the wafer surface where they penetrated. Okay, if we compare these two diagrams, we can conclude that in case of thermal doping, the concentrations, the highest concentrations, thermal diffusions, the highest concentrations is the surface, is at the surface, but for ion implantation the highest concentrations of dopant just below the surface, okay.